This is a demonstration of running the adjoint method in MachLine. Uh, I have here a delta wing mesh that I created in OpenVSP, and I exported the STL. It's pretty coarse. It's got 500 points, but let's run this in MachLine. To do that, you need to have an input JSON structured in this way, and you can reference the MachLine GitHub. There's a wiki section that gives the input file structure. So we're running this at 4 degrees angle of attack at Mach 2. And what I've added here is adjoint sensitivities and calc adjoint under geometry. So if you don't add these, it will default to false and it'll run MachLine as normal without calculating the adjoint method or without running the adjoint method. So let's do that. We'll run it without adjoints. Here in the command prompt, you can see I've navigated to the MachLine directory, and I ran the make command to compile MachLine. Now I will run MachLine and give it the path to the input file. So it ran in just about half a second. Let's go back to pair view. We can look at the results, the output VTK that MachLine produces. And these are all the different data sets that MachLine is output. We're looking at the pressure map. It's a pretty coarse mesh, but you can still see the effect of the bow shock in this pressure map on the back of the wing. So now let's run this mesh with adjoints being calculated. We will set this to true and then run the same input. And it should take a bit longer. It should take about 20 seconds with this mesh size. And you can see there's a few more things being printed to the screen telling you how the results from the adjoint method. These are all the sensitivity values, and it ran in about 20 seconds. So let's go back to pair view and reload our VTK. And you can see now we have a few more options of data sets to plot. We have sensitivity vectors for the X, Y, and Z force coefficients. And each one of these sensitivity vectors has another set for X, Y, and Z. And whenever plotting the adjoints, you need to make sure that, or it's best to make sure your color map is centered around 0. So I'll go from negative 0.1 to 0.1. So this way, I can tell from red areas are positive values of sensitivities and blue areas are negative. And so this tells me that moving mesh points in the up or positive Z direction will increase my Z force coefficient, and moving mesh points in the negative Z direction, or indicated by the blue areas, that will also increase my Z force coefficient. And if you moved them in the opposite direction of the color indicated, that would decrease your force coefficient. So again, this is pretty coarse, and I'll show you real quick. As you increase the number of mesh panels, your sensitivity map converges to a certain pattern. And I ran this 15,000 panel case previously. So I'll show you the results of that. Let's go back to the ZZ. center the color map around 0. There we go. So now you can see a bit finer detail, and you can make draw interesting conclusions from looking at the different maps. Let me center this one real quick. So this map shows that if I move red areas in the positive Y direction and blue regions in the negative Y direction, that will increase my side force in the Y direction. And you can see with this, these colored areas are in the same region as where that shock was. So this is indicating that I can use that to create more side force. And so there's 9 total maps. And you can draw different conclusions from each one. But all this data is perhaps better used as an input to a gradient-based optimization. So that is the demonstration of how to run the adjoint method.